Welcome to this problem walkthrough on missing element in sorted array. In this session, we'll explore an interesting problem that involves finding a missing number in a sorted sequence. We'll discuss the problem, break it into manageable parts, and analyze the approaches to solve it. Let's dive in. Imagine you are given an array of integers called nums, where the numbers are sorted in strictly increasing order. Alongside this array, you are also given an integer k. Now, within the range defined by the first element of nums, which is nums, 0, and the last element, nums, -1, there are some numbers that are missing. Your job is to find the kth missing number in this range. If the number of missing integers within this range is less than k, you will need to extend the range beyond nums, -1, until you locate the kth missing number. For the input format, the problem gives you this sorted array, nums, and the integer k. In terms of output, you will simply return the kth missing number as an integer. Remember, since the array is strictly increasing, all missing numbers will naturally fall between or beyond the range of the given elements. Let's break this down with an example. Suppose the input array is nums equals 4, 7, 9, 10, and k equals 1. The range defined by the values in nums is from 4 to 10. As we look for missing numbers in this range, we find that the numbers 5, 6, and 8 are not present in the array. If we are tasked with finding the first missing number, that would simply be the first value in this list of missing numbers, which is 5. So the output for this input would be 5. Now, let's consider a similar input, nums equals 4, 7, 9, 10, but this time with k equals 3. Again, the missing numbers within the range, 4, 10, are 5, 6, and 8. Since we are looking for the third missing number, the result is 8. To explore this further, let's take another example. This time, the input array is nums equals 1, 2, 4, and k equals 3. The range defined by the array is 1, 4, and the only missing number within this range is 3. However, since k equals 3 and there is only one missing number in this range, we need to continue searching beyond the end of the array, which is 4. The next missing numbers after 4 are 5 and 6. So, in total, the first three missing numbers are 3, 5, and 6. The third missing number in this sequence is 6, and that is the output. This demonstrates how the solution must handle cases where k exceeds the count of missing numbers in the range of the given array. Now, let's consider the problem's constraints and edge cases. The length of the array, nums, can range from 1 to 50,000, and each element in the array is guaranteed to be a unique integer between 1 and 10⁻7. The integer k, representing the position of the missing number defined, can be as large as 10⁻8. It's also important to note that the array is sorted in strictly increasing order, which simplifies the process of identifying missing numbers. Some important edge cases to consider include scenarios where k is larger than the total number of missing numbers within the range of the array. In such cases, the solution must correctly extend the range beyond the last element of the array. Additionally, when the array has very few elements, such as just 2 numbers, the solution must still be able to calculate the missing numbers within this small range. Since the input guarantees no duplicates or unsorted arrays, we do not need to handle any invalid cases of input. These constraints and edge cases ensure that our solution is robust and efficient for all valid inputs. To approach this problem, we first consider a brute force method using an iterative search. The idea here is straightforward. We count each missing number explicitly by iterating through the range between the first and last elements of the sorted array. Starting with the first element, we check if each number in the range exists in the array. If it doesn't, we increment a counter, and once the counter reaches k, we return that number as the kth missing element. While this method is simple and intuitive, it has significant drawbacks. Its time complexity is proportional to the product of the range of numbers and the size of the array, making it inefficient for larger inputs. Furthermore, since it doesn't require additional memory, the space complexity is 1. However, the inefficiency of iterating over a potentially large range makes this approach impractical for larger datasets. Now, to improve efficiency, we can take advantage of the sorted structure of the array and use a binary search approach. The key insight here is that we don't need to explicitly check every number. Instead, we calculate the number of missing integers up to any given index using the formula missing I equals nums I minus nums 0 minus I. With this, we can determine whether the kth missing number lies before or after a particular index. By narrowing the search range using binary search, we can efficiently find the correct position. For example, the total number of missing elements in the range can be calculated as nums-1 minus nums 0 plus 1 minus the length of the array. If k exceeds this total, the missing number lies beyond the last element of the array. Otherwise, binary search helps us pinpoint the smallest index where the missing count meets or exceeds k. Once we identify this index, we can use the formula nums I1 plus k minus missing I1 to compute the kth missing number directly. This binary search approach has a significant advantage in terms of efficiency. Its time complexity is logarithmic, O log n, due to the binary search process, and it maintains a space complexity of O1. This makes it highly suitable for large input sizes, as it avoids the inefficiencies of iterating through an entire range. However, it does require an understanding of the missing function and the binary search logic, which might make it slightly less intuitive for beginners. Additionally, there is an alternative method using a linear scan. In this approach, instead of iterating through the entire range of numbers, we traverse the array and track the count of missing numbers on the fly. By comparing the difference between consecutive elements, we determine how many numbers are missing and stop as soon as the count matches k. While simpler than binary search, this method is less efficient for larger inputs, as its time complexity is linear, O(n). The linear scan approach, while straightforward, still has limitations when compared to binary search. It processes the array sequentially, so its time complexity is O(n), which is less efficient for larger datasets. Like the other methods, it maintains a space complexity of O(1), so it doesn't require additional memory. After evaluating all three methods, the optimized binary search approach stands out as the best choice for this problem. By leveraging the sorted nature of the array, it minimizes the computational workload and performs well even for large inputs. While the brute force and linear scan methods are simpler to implement, their performance scales poorly with input size, which makes them less suitable for competitive programming or real-world scenarios with large datasets. The binary search method, although slightly more complex, achieves the best balance of efficiency and scalability. When considering space efficiency, all three approaches have a space complexity of O(1), which means that memory usage is not a distinguishing factor. The choice of approach, therefore, depends purely on time efficiency. Given this, the binary search approach emerges as the optimal solution. It balances all critical factors, offering the best performance for finding the kth missing number in a sorted array. By focusing on the number of missing elements up to any given index, it avoids unnecessary computations and reduces the search space effectively. This makes it not only the most efficient solution but also the most practical one for scenarios involving large inputs. Overall, the binary search approach provides both speed and reliability, making it the preferred strategy for solving this problem efficiently. The problem involves finding the kth missing positive integer in a sorted array of unique integers called nums. Let's break it down with an example. If the array is 2, 3, 4, 7, 11, and k is 5, the missing numbers are 1, 5, 6, 8, 9, 10, and the fifth missing number is 9. To solve this using a brute force iterative approach, we start by initializing a few variables. First, we set missing_count to 0, which will track how many numbers are missing. Then, current is set to 1, representing the first positive integer to check. Lastly, we use an index pointer I to track our position in the array nums. The idea is to iterate through all positive integers, checking whether each one is missing from the array or not. If it is missing, we increment the missing_count. If it is present, we move the pointer I to the next number in the array. This process continues until missing_count reaches k. The process ends when the count of missing numbers equals k. At this point, the current value of current is the kth missing number, and we return it. There are a few edge cases to consider. If the array nums is empty, then the result is simply k because there are no existing numbers to skip. Another edge case occurs when k is larger than the range of missing numbers within the array. For example, if the largest number in nums is smaller than the total number of missing integers needed to reach k, we must continue counting missing numbers beyond the array's end. The key insight here is that the array's sorted nature allows us to efficiently track which numbers are missing. By sequentially checking integers starting from 1, we can determine which numbers are absent from the array and increment our count accordingly. While this brute force approach works, it has opportunities for optimization, such as calculating gaps between consecutive elements in nums instead of iterating through every number. This approach uses a few core data structures and variables. The array nums contains the sorted input data. The variable missing_count tracks how many missing integers have been found so far. The variable current represents the integer currently being checked, and the variable I is a pointer to the current index in the array. Let's walk through an example. Given nums equals 2, 3, 4, 7, 11, and k equals 5, we initialize missing_count equals 0, current equals 1, and I equals 0. We compare current equals 1 with nums, I equals 2. Since 1 is less than 2, it's a missing number. We increment missing_count to 1 and current to 2. Next, we compare current equals 2 with nums, I equals 2. Since they are equal, 2 is not missing, so we move the pointer I to the next index and increment current to 3. Repeating this process, we find that 3 and 4 are also present in the array, so we continue moving the pointer and incrementing current. When current becomes 5, it's less than nums, I equals 7, meaning 5 is missing. We increment missing_count again. As we continue, the next missing number is 6, bringing the missing_count to 2. Incrementing further, we encounter 8 and 9 as additional missing numbers. Once the missing_count reaches 5, the process stops, and we return 9 as the fifth missing number. The brute force algorithm has a time complexity of O, max, n, k, where n is the size of the array and k is the position of the missing number we are looking for. In the worst case, if k is very large, we may need to iterate up to the kth missing number, even beyond the range of the given array. For smaller values of k, the runtime depends on the range of numbers checked, which is determined by the array size. The space complexity is O(1), since we only use a few integer variables, and no additional data structures are required. This makes the algorithm memory efficient but potentially slow for larger ranges. To optimize this approach, we could take advantage of the gaps between consecutive elements in the array. By pre-computing the number of missing integers in these gaps, we can skip over large ranges of numbers instead of checking each one individually. For an even faster solution, we could use binary search to pinpoint the kth missing number directly, but that would deviate from the brute force approach we're focusing on here. Let's also revisit the edge cases. If the array is empty, the output is simply k, as all numbers are missing. If k is smaller than the smallest element in nums, the result lies entirely before the array, so we can return k directly. Finally, when k is very large, we must continue counting missing numbers beyond the largest element in nums until we reach the kth missing number. These considerations ensure our solution handles a wide range of scenarios effectively, even with the brute force method. This implementation solves the problem of finding the kth missing positive integer in a sorted array with a combination of binary search and arithmetic calculation. Here's the step-by-step breakdown. 1. Helper function missing_count*. This function computes how many numbers are missing up to a given index IDX. It uses the formula nums, IDX, nums, 0, IDX, which calculates the difference between the expected value, assuming no gaps, and the actual value in the array. 2. Edge case for missing beyond array*. If the kth missing number is greater than the total missing numbers within the range of the array, it is calculated by extending beyond the array. The function directly computes the result as nums-1 plus k missing_count, n1. 3. Binary search setup*. The binary search is used to locate the smallest index where the kth missing number lies. Variables left and right are initialized to the start and end of the array, respectively. For binary search execution*, the loop continues while left-right. At each step, the middle index mid is calculated. If the number of missing elements at mid is less than k, the search moves to the right, left equals mid plus 1. Otherwise, it narrows the search to the left, right equals mid. 5. Final calculation asterisk. After determining the correct index, the kth missing number is calculated using the formula nums, left 1, plus k missing underscore count, left 1. This computes the missing number based on the previously found index. This approach is efficient, with a time complexity of O log n due to binary search, making it suitable for large input sizes. The code handles edge cases, such as when the kth missing number is beyond the last element of the array, ensuring robustness and correctness. Here, we begin by defining a Java class called solution and implementing the method missing element, which takes an array of sorted integers nums and an integer k as input. The goal is to find the kth missing number in the sequence implied by nums. To assist with this, we create a helper function called missingCount. This function calculates how many numbers are missing from the beginning of the array up to a given index idx. The calculation is based on the difference between the value at nums, idx, and nums, 0, adjusted by subtracting the index itself, which accounts for the expected consecutive sequence. Next, we store the length of the array in the variable n. If the kth missing number is located beyond the bounds of the array, we calculate it directly by taking the last number in the array, nums, n1, and adding the difference between k and the total count of missing numbers in the entire array. This ensures we handle cases where the missing number lies past the range of the input array. For cases where the kth missing number is within the array's range, we use binary search to efficiently locate the smallest index where the kth missing number resides. We initialize left to 0 and right to n1, setting up the bounds for our binary search loop. Within the binary search loop, we calculate the middle index, mid, using the formula left plus right left /2 to prevent potential overflow. If the count of missing numbers up to mid is less than k, it means the kth missing number must lie further to the right, so we adjust left to mid plus 1. Otherwise, we adjust right to mid to narrow the search space towards the left. Once the loop terminates, left will point to the smallest index where the kth missing number is located. Finally, we calculate the kth missing number based on the number at nums, left 1, and the difference between k and the count of missing numbers up to left 1. This gives us the desired result, which is returned as the output of the method. The implementation is efficient, leveraging binary search to reduce the time complexity to O log n for the main search process. To solve this problem, we start by defining a helper function called missing_count. This function calculates how many numbers are missing from the sequence up to a given index idx. The formula is missing_count, idx equals nums, idx, nums, 0, idx, which essentially measures the gap between the actual value at nums, idx, and the expected value if there were no missing numbers up to that index. Next, we need to determine if the value of k exceeds the total number of missing elements in the entire array. Here, the length of the array, n, is 4, and the total missing count at the last index, missing_count, 3, is calculated as 10, 4, 3 equals 3. Since k equals 1 is less than or equal to this total, we know the kth missing number falls within the range of the array, and we can proceed with binary search. The goal of the binary search is to find the smallest index where the kth missing number could lie. We initialize left to 0 and right to 3, the bounds of the array. First, we calculate the midpoint as mid equals left plus right //2, which gives 1. At this midpoint, missing_count 1 equals 7, 4, 1 equals 2. Since this value is greater than or equal to k equals 1, we update right to mid, narrowing our search range. Then, we recompute the midpoint as mid equals 0 and find that missing_count 0 equals 0, which is less than k. This means we adjust left to mid plus 1, making it 1. Now that we've narrowed down the search, we calculate the kth missing number. Since left is 1, we look at the value just before it, which is nums, 0, equals 4. The number of missing elements up to this index, missing_count 0, is 0. Using these values, we calculate the result as nums, 0, plus k missing_count 0 equals 4 plus 1, 0 equals 5. So, the kth missing number in this example is 5. For a second example where nums equals 4, 7, 9, 10, and k equals 3, the total missing count at the last index is 3. Since k matches this total, the missing number lies beyond the array. We calculate it directly as nums, -1, plus k missing_count 3 equals 10 plus 3 equals 10. The final output here is 10. In a third example, nums equals 1, 2, 4, and k equals 3. The total missing count at the last index is 1, which is less than k. This indicates the kth missing number also lies beyond the array. We compute it as nums-1 plus k missing underscore count 2 equals 4 plus 3 1 equals 6. The result for this case is 6. The time complexity of this algorithm is primarily driven by the binary search process. Since binary search operates on a sorted array and reduces the search space by half in each step, the number of iterations is proportional to the logarithm of the array size, giving us a time complexity of O log n. Additionally, there's the helper function missing underscore count, which calculates the number of missing elements up to a specific index using simple arithmetic operations. This function runs in constant time, or O1, and is invoked during each iteration of the binary search. Since binary search itself runs for O log n iterations, the total contribution of this helper function is O log n asterisk O1, which simplifies to O log n. Outside of the binary search loop, there's a constant time check to handle cases where the kth missing number lies beyond the array's range. This adds O1 time, but it does not affect the overall complexity since binary search dominates the runtime. Therefore, the time complexity of the entire algorithm is O log n. The space complexity of the algorithm is minimal because it doesn't make use of any additional data structures. The input array nums is provided as input and doesn't count toward extra memory usage. The helper function missing underscore count uses only arithmetic operations and doesn't require additional memory. All the variables used in the algorithm, like n, left, right, and mid, are scalar values, meaning their memory usage is constant, or O1. As a result, the total space complexity of the algorithm is O1. Now, if we compare this to a brute force approach, a naive method would involve iterating through the array and counting missing integers sequentially. This would require a complete scan of the array, resulting in an O(n) time complexity significantly less efficient than the binary search approach. The optimized solution makes use of pre-computed values for the number of missing integers at any given index and leverages binary search to narrow down the search space logarithmically, making it far superior to the brute force alternative. When analyzing the best, average, and worst cases, we see that the algorithm performs efficiently across the board. In the best case, the kth missing number is beyond the largest number in the array. Here, the algorithm simply computes the result in constant time, or O1. On average, the kth missing number will lie somewhere within the array. This requires the use of binary search, leading to an average time complexity of O log n. In the worst case, the kth missing number is located near the end of the array, just before the largest element. Even in this case, binary search still runs in O log n time. To understand why binary search is so efficient, consider its mechanics. It splits the array into two halves at each step, reducing the search space by half with each iteration. For an array of size n, the number of iterations required is proportional to log 2, n, which confirms the O log n time complexity. Since the helper function operates in O1 time and is only called during each binary search iteration, the overall complexity remains O log n. In summary, the algorithm achieves O log n time complexity and O1 space complexity, making it highly efficient compared to the brute force method, especially for large arrays, where the logarithmic time complexity of binary search provides significant performance gains. When working on this problem, there are a few common mistakes to watch out for. First, overlooking edge cases can lead to incorrect results. For instance, if the array starts at a number like 5, you need to account for missing numbers at the beginning, such as 1 through 4. Next, inefficient brute force approaches can slow down your solution significantly. For example, iterating through the entire range to count missing numbers results in an O(n plus k) time complexity, which is unnecessary for large inputs. Additionally, if the array contains duplicates, despite the problem specifying a distinct, sorted array, failing to validate this could cause logic errors. Finally, off-by-one errors are a frequent issue when calculating missing numbers, especially when transitioning between zero-based and one-based indexing. To avoid this, always double-check your calculations and indexing logic carefully. Another potential pitfall is not considering space constraints. Generating large auxiliary arrays to store missing numbers can lead to memory issues, so it's often better to explore constant space solutions. Now, in interviews, it's worth highlighting that binary search is a highly effective optimization for this problem. Because the array is sorted, binary search can reduce time complexity from O(n) to O log n. To use this effectively, it's important to understand the relationship between array indices and missing numbers. For example, the number of missing elements up to any index I is calculated as I plus 1. Also, when tackling variations of this problem, always clarify constraints and edge cases upfront. This includes asking about array bounds, whether duplicates are possible, and if the input is guaranteed to be sorted. Lastly, be prepared to discuss trade-offs. While a brute force approach is simpler, it's slower. A binary search solution, on the other hand, is much faster but requires a deeper understanding of the problem structure. This problem is closely related to several others that you might encounter. Examples include LeetCode 1539, which focuses on finding the kth missing positive number, LeetCode 1060, which is about missing elements in sorted arrays, LeetCode 268, which deals with finding a single missing number, and LeetCode 287, which involves detecting duplicates in arrays. Now, in terms of alternative approaches, one option is brute force through an iterative search. This has a time complexity of O(n plus k) and a space complexity of O(1). While it's simple to implement, it's not efficient for large arrays. A more efficient solution involves binary search on the missing count, with a time complexity of O log n and a space complexity of O(1). This approach requires identifying the missing count up to any given index, which can be a key insight for solving this problem efficiently. The trade-off here is that while binary search is faster, it requires a deeper understanding of the array structure and the logic behind missing numbers. Finally, let's talk about an alternative approach that can be particularly useful for unsorted arrays: hashing. By using a hash set, you can achieve a time complexity of O(n), while ensuring that the space complexity is also O(n). This method is effective when the input array is unsorted, and you need a quick way to track missing numbers. However, it's not ideal for situations where memory constraints are tight, as the additional space required for the hash set can be significant. Each of these approaches, brute force, binary search, and hashing, has its own advantages and trade-offs, so it's important to choose the right one based on the problem's constraints and the given input. Thank you for joining this walkthrough of the missing element in sorted array problem. We summarized the key points, explored algorithmic insights, and discussed when to use different approaches. Keep practicing, stay curious, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!